Ask an ordinary person how an AI company makes money, and the answer sounds simple. Build a brilliant model, charge people to use it, and scale like software. That explanation feels logical, because software usually becomes extraordinarily profitable once the expensive development work is finished, and each additional customer costs almost nothing. But a ChatGPT-style company does not merely sell finished software. Every question forces the company to manufacture a fresh answer using costly computing infrastructure. The product looks like an app, but economically it behaves more like an electricity utility, a cloud factory, and a research laboratory operating at the same time. That contradiction creates the central question behind the entire industry. Can AI companies grow revenue faster than the cost of training, serving, and constantly replacing their models? The answer matters because an AI company can attract hundreds of millions of users, dominate public attention, and still lose money whenever those users become more active. In most internet businesses, more engagement is automatically good news. In generative AI, more engagement can produce both more revenue and a much larger computing bill. A free social network can display another advertisement, while a search engine can monetize another query. But a chatbot must first pay to generate the response it hopes to monetize. Means the most popular AI model is not necessarily the healthiest business, and the smartest model is not necessarily the most profitable one. To understand why, we have to follow one ordinary prompt from the moment a user presses enter to the moment the company either earns a margin or absorbs a loss. Suppose you ask an AI model to summarize a long contract, explain a medical paper, or write several pages of computer code. The model first converts your words into tokens, which are small units of text that computers can process mathematically. A short word may become one token, a longer word may become several, and punctuation or fragments can also count toward the total. The company usually measures the input you send, and the output the model generates, then charges according to how many tokens move through the system. OpenAI's current API pricing illustrates the structure clearly. Output tokens for frontier models can cost several times more than input tokens. That is not an arbitrary pricing trick, because generating each new output token requires the model to repeatedly calculate what should come next. A long response, therefore, consumes more computing time than a short response, even when both begin with the same question. Reasoning models can be even more expensive, because they may perform additional internal computation before presenting the answer that the user finally sees. The viewer sees one clean paragraph, while the provider may be paying for a much longer invisible process running inside a data center. That creates the first counterintuitive rule of AI economics. Proving the answer can make the product more valuable while simultaneously making each interaction more expensive. The company can respond by charging more, limiting usage, using a cheaper model, or hoping that engineering improvements reduce the cost before customers notice. Every option contains a trade-off. Because higher prices reduce adoption, tighter limits frustrate users, cheaper models may feel worse, and efficiency gains are quickly copied by competitors. The result is a business where price, quality, speed, and computing cost are continuously pulling against one another. This is very different from selling one permanent software license. The company never finishes producing the product. The cost of one response also depends on factors the user rarely sees, including model size, context length, hardware type, batching efficiency, and whether earlier text can be reused. A larger model may deliver better judgment, but it generally requires more memory, more chip time, and more electricity than a smaller, specialized model. Long context windows create another cost, because the system may need to process thousands of pages before producing the first useful sentence. Providers reduce this burden through caching, which allows repeated information to be stored and processed more cheaply when it appears again. They also batch requests, route simple tasks to smaller models, compress prompts, and reserve expensive reasoning for the moments that genuinely need it. Techniques sound like engineering details, but they determine whether the same subscription produces a profit or a loss. The economic advantage may therefore belong to the company with the best routing system rather than the company with the single highest benchmark score. One model can even serve as a manager that decides which cheaper model, tool, database, or human specialist should handle each part of the job. This changes the product from one giant brain into an orchestrated workforce of differently priced components. The provider is no longer optimizing only intelligence, optimizing the cost of delivering enough intelligence for each request. The model must answer again tomorrow, and the company must pay again tomorrow. Training creates the second major expense, and it begins long before a model answers its first paying customer. Developers collect and clean data, design experiments, hire researchers, run smaller tests, evaluate failures, and repeatedly adjust the system before the final training run. The public often hears one dramatic estimate for the final training run, but that number can exclude months of experiments, staff compensation, failed attempts, and supporting infrastructure. Hawk AI estimates that the cost of frontier training runs has grown rapidly, with the largest runs potentially exceeding $1 billion by 2027 if historical trends continue. That projection is an estimate rather than a guaranteed outcome. Chip efficiency, model architecture, training methods, and corporate strategy can all change the trajectory. Even so, the direction is clear. Competing at the frontier increasingly requires access to capital on the scale of major infrastructure industries. Hardware represents much of the burden, but expensive researchers, experiments, networking equipment, and electricity also contribute to development costs. The finished model then begins depreciating almost immediately, not because it physically breaks, because competitors release systems that are cheaper, faster, or more capable. A model can remain technically impressive while becoming commercially unattractive within months. It resembles the economics of a blockbuster movie that requires another blockbuster sequel before the first film has fully recovered its cost. The company is therefore not investing once in a durable product, financing a permanent race in which the finish line keeps moving. Training receives the headlines, but inference may become the more important expense because it repeats every time anyone uses the product. Inference is the process of running the trained model to generate new outputs, and it transforms user activity directly into operating cost. Hawk AI's 2026 analysis of several AI companies estimated that research and inference compute together represented more than half of total expenses. The precise percentage varies by company and relies partly on estimates. The broader lesson is difficult to avoid. Compute is not a side expense. It is the raw material consumed by the product. This leads to a revealing comparison with traditional software as a service businesses. A normal SaaS product may spend heavily to build a platform, but serving the next customer often requires only a small amount of additional computing. An AI model provider may spend heavily to build the model and then continue paying meaningfully whenever the next customer generates text, images, audio, video, or code. The marginal cost may fall over time, but it does not disappear. Why subscriptions can be dangerous when usage is unlimited. A light user may pay $20 and consume only a small fraction of that amount in compute, creating a healthy margin. A heavy user may pay the same $20 while running long research sessions, generating code, creating images, and forcing the company to spend far more. The company is effectively averaging profitable customers and expensive customers together, hoping the first group subsidizes the second. This is similar to a gym membership, except the heaviest user does not merely wear out a treadmill. That user may consume scarce chips and electricity every hour. Usage limits, message caps, priority tiers, slower service during congestion are therefore not random annoyances. They are economic controls designed to prevent one subscription from becoming an unlimited claim on expensive infrastructure. Free tier creates an even stranger equation. Because the company knowingly serves users who may never pay. Why would any rational business do that? Because free users can create distribution, brand dominance, product feedback, habit formation, future pool of subscribers or enterprise employees. A student who uses a free chatbot today may later request the same product at work, pay for a premium plan, or build an application through the API. Free usage can therefore function like marketing. But unlike a normal advertisement, the marketing expense increases every time the prospect engages more deeply. The best possible free user is highly engaged, because engagement creates attachment and future revenue. Worst possible free user is also highly engaged, because engagement creates a large inference bill without any guarantee of conversion. The company cannot know with certainty which version it is funding until later. Enterprise customers improve the equation because they usually pay more, sign longer contracts, and value security, support, administration, and integration beyond raw model intelligence. A company may tolerate low-margin consumer usage if it creates brand awareness and helps win high-value corporate accounts later. Enterprise revenue can also be more predictable, but the sales cycle is slower, and implementation costs can be substantial. Large customers demand reliability guarantees, data controls, legal review, custom deployment, and technical support that consumer subscriptions do not provide. This means higher contract value does not automatically translate into higher margin. For BI, customers create a different pattern because they pay according to usage, allowing the provider to pass more of the inference cost directly to the buyer. Use SIDS-based pricing protects the provider from extreme users, but it makes customer bills less predictable and encourages developers to switch whenever a cheaper model appears. Consumer subscriptions favor simplicity, APIs favor cost alignment, and enterprise contracts favor predictability. So no single revenue model solves every problem. The healthiest company may combine all three, using each customer group to balance weaknesses in the others. That diversification matters, because a sudden pricing change or customer loss in one segment can otherwise damage the entire company. Uncertainty explains why AI businesses search for several revenue streams rather than relying on one monthly consumer subscription. They can charge consumers, sell API tokens to developers, license enterprise software, provide cloud infrastructure, customize models, and bundle AI into existing products. Some companies may eventually use advertising, transaction fees, commissions, or outcome-based pricing, but those models remain unevenly developed. Parent customer can also differ from the real economic customer. A consumer may use the model for free, while an employer pays for enterprise access and a cloud provider finances the infrastructure through a partnership. Makes the business less like one app and more like a layered ecosystem in which each participant pays for a different kind of value. Consumers pay for convenience, developers pay for programmable intelligence, enterprises pay for security and workflow integration, and infrastructure partners pay for strategic demand. The model itself may become the least profitable layer if competition drives token prices toward the cost of compute. Stanford's AI Index found that the price of obtaining GPT 3.5 level performance fell more than 280-fold between late 2022 and late 2024. That was excellent news for users and developers, but it was also a warning for companies hoping that today's premium prices would remain permanent. Hardware improves, algorithms become more efficient, smaller models become stronger, and competitors rapidly match capabilities that once appeared exclusive. 2026 AI Index also reported that leading model performance had become increasingly clustered, shifting competition toward cost, reliability, speed, and specialized usefulness. When several models feel similarly capable, customers gain bargaining power and switching becomes easier. That can produce a commodity trap. The industry spends more to build better models while customers pay less for each unit of intelligence. Open-weight models intensify the pressure because companies can download, modify, and sometimes run capable systems on their own infrastructure. These models are not always free to operate, but they can reduce dependence on one provider and make premium API pricing harder to defend. A closed provider must therefore justify its price through better performance, safety, tools, reliability, support, or convenience. If the performance gap narrows, the remaining advantages must carry more of the economic burden. This resembles the database and cloud markets, where open alternatives coexist with highly profitable managed services. Customers often pay not because they cannot access the underlying technology, because they do not want to operate, secure, update, and scale it themselves. The profitable product may therefore be dependable delivery, rather than exclusive ownership of the model. Data can provide another advantage. Value is frequently misunderstood. More conversations can reveal failure patterns and product needs, yet privacy rules and customer trust limit how that information can be reused. The company must learn from usage without making customers feel that their confidential work has become training material. The company may escape by owning something competitors cannot easily copy, such as distribution, proprietary data, trusted enterprise relationships, custom chips, or a dominant platform. This is where the economics of a pure model laboratory begin to diverge from the economics of an integrated technology giant. A laboratory must earn enough directly from its models to finance research and inference. An integrated company can use AI to strengthen advertising, cloud computing, productivity software, devices, commerce, or customer retention elsewhere. The model may be costly on its own, while still creating profit across the wider system. Google's Gemini strategy provides one of the clearest public examples of this integrated approach. Google's path began with years of investment in custom tensor processing units, data centers, research teams, and products that already reached billions of users. When generative AI demand accelerated, the company did not need to create an entirely new distribution network from nothing. It could place AI inside search, productivity tools, cloud services, mobile devices, and paid subscriptions where customers already spent money. That reduces customer acquisition cost, one of the largest hidden expenses for a standalone consumer technology company. It also creates several ways to recover the same infrastructure investment. A server supporting model training today may later support cloud customers, search features, advertising systems, or internal productivity workloads. Capacity can still be wasted, but the company has more options for redirecting it than a laboratory built around one product. Alphabet's cloud business also reported strong growth and a rising operating margin. Although public filings do not isolate exactly how much profit came from generative AI. That limitation is important because companies often announce adoption, bookings, or revenue without disclosing the complete cost required to produce it. A model can generate impressive sales and still earn a weak return after depreciation, electricity, research support, and customer acquisition are included. Alphabet reported that the Gemini application had more than 750 million monthly active users by the end of 2025. It also reported more than 8 million paid seats for Gemini Enterprise only months after launch. Those figures demonstrate adoption, but adoption alone does not answer whether the model itself earns an attractive return. The more revealing number was Alphabet's claim that it reduced Gemini serving unit costs by 78% during 2025 through optimization, efficiency, and better utilization. Serving unit cost means the expense required to deliver a defined amount of AI output, and reducing it changes the economics of every future interaction. Reduction of that size can turn previously unprofitable usage into profitable usage without raising the price paid by customers. It can also allow the company to lower prices, increase free access, or offer more capable models while protecting margins. Savings may not stay with the provider for long, because competitors can respond with their own efficiency gains and lower prices. This is the AI version of Jevons paradox. Making computation cheaper can increase total demand so dramatically that overall spending still rises. Cheaper answers encourage longer conversations, more agents, more automated workflows, and entirely new products that were previously too expensive. A company saves money on each token, but may serve billions more tokens. Alphabet's infrastructure spending shows the scale of that effect. The company reported approximately $91 billion of capital expenditure in 2025, and projected between $175 and $185 billion for 2026. It said most of the investment would support technical infrastructure, servers taking the largest share and data centers, plus networking taking the rest. Alphabet is not spending all of that solely on Gemini, because the same infrastructure supports search, cloud customers, advertising systems, and other services. Shared use is precisely the advantage. The company can spread infrastructure costs across many profitable businesses, develop custom chips, control the software stack, and redirect capacity as demand changes. A standalone AI laboratory may have access to powerful partners, but it usually cannot internalize all of those benefits. This does not prove that integrated companies will automatically win, because focused laboratories may innovate faster, attract stronger talent, and build products users prefer. It does reveal that two companies can operate equally capable models while facing completely different paths to profitability. The next complication is that model intelligence can increase cost faster than customers' willingness to pay. A system that reasons longer, uses tools, searches the web, reads enormous files, and checks its own work may deliver a superior result. Yet the customer may still expect the answer inside the same $20 subscription. The company then faces a choice between absorbing the extra cost, restricting the feature, moving it into a premium tier, or simplifying the experience. This decision can affect growth, reputation, and competitive position. This creates a dangerous chain reaction when competition becomes intense. One company launches a more capable model, forcing rivals to spend more on training and offer similar capabilities. The rivals cut prices or expand free access to prevent users from leaving. This site rises, inference demand expands, and every provider needs more chips, power, and data center capacity. Capital expenditure climbs before the companies have proven that the new usage will generate enough revenue. Lower prices then reduce revenue per token, which requires still more volume to justify the infrastructure. The industry can therefore grow spectacularly, while individual companies remain financially fragile. Profitability also depends on accounting timing, because infrastructure is purchased up front, while revenue may arrive slowly over several years. A company can report strong cash outflow during expansion even if future contracts are valuable, or show improving gross margin while still spending heavily on research. Makes simple claims that an AI company is either obviously profitable or obviously doomed less reliable than they appear. Correct question is whether each generation of investment creates durable revenue, before the next technological cycle demands another round of spending. Investors must separate temporary losses caused by rapid expansion from structural losses caused by selling intelligence below its true production cost. The first can eventually improve with scale, while the second becomes more dangerous as usage grows. Distinction is difficult to observe from outside because private laboratories disclose limited financial detail and often depend on reported estimates. Any confident forecast should therefore acknowledge uncertainty rather than treating incomplete numbers as audited facts. The optimistic interpretation is that this resembles the early cloud era, when massive infrastructure spending eventually created highly profitable platforms. The pessimistic interpretation is that models become interchangeable faster than providers can recover their training and infrastructure costs. Both outcomes can occur simultaneously, with a few platforms earning extraordinary returns while many laboratories disappear, merge, or become suppliers. The best-case outcome for a ChatGPT-style company combines high consumer adoption, enterprise contracts, inference, strong developer demand, and defensible distribution. In that scenario, training costs remain enormous, but each new generation creates enough additional value to expand revenue faster than total spending. A realistic successful outcome may look less spectacular. The company becomes a strong platform with lower margins than traditional software, but enormous strategic importance. The realistic negative outcome is price compression, heavy customer concentration, recurring capital needs, and dependence on infrastructure partners. The failure scenario occurs when usage grows without sufficient monetization, new models arrive before old investments are recovered, and lenders or partners stop financing the gap. The service may remain popular even as the company behind it becomes financially unsustainable. That is the final correction to the popular mental model. An AI model is not merely software that becomes free to distribute after development. A continuously operating production system that turns chips, electricity, research, data, and capital into intelligence on demand. The winners will not simply build the smartest model. They will build the system that produces useful intelligence at a cost customers will repeatedly pay. ChatGPT-style companies can make money, but only when the value of every answer grows faster than the hidden machinery required to create it.